All right, good morning, everyone. Today we're going to be covering the concept of deep learning with PyTorch, and we're going to actually create something called a neural network. We're going to go over tensors. What is a neuron? We're going to talk about weights and biases and how neurons relate to one another. And then we'll go through the process of how we would feed in data into a neural network in order for that data or that model of the neural network to actually be able to output some sort of a guess, because that's what deep learning and machine learning really is. It's essentially just guessing. For lack of better words, the best um, figurative example that I could think of when it comes to machine learning is you quite literally grab an entire pan. I would think of like a pan that you would put fries on, right? You put a bunch of stuff that would stick onto the wall, and then you just throw it at the wall. And then you figure out what sticks that you wanted it to stick and what stick that you didn't want to stick. And then you try to adjust the adhesive in your material to try to get it right? You're just consistently throwing stuff at the wall, changing the amount of glue that you want in each independent element. That way, whenever you throw it at the wall, only the correct information will stick to the wall and the rest of it will fall. And then Tony, I'm liking the Bane mask. I didn't see that until now. Is that made out of Legos?
It's 3D printed.
Oh, that's awesome. All right. Okay, let's go ahead and continue moving forward here. This is going to be deep learning. This is what we'll create today. This picture will make a lot of sense later on. But before we start even talking about deep learning and everything that works with PyTorch, we also have to talk about data. All right, well, what is data? We've talked about data in the sense of t text pre-processing, but we haven't talked about data in its numerical format because it's the only way the machines can actually learn. It's by data that comes in through numbers. So this is going to be the model that we'll create today. We're going to create a model that's able to take in the CSV data, and it's going to accurately be able to tell us what kind of grade a student would receive in a class. Now, all these numbers and everything really don't tell me anything, um, because it's not telling me, hey, what does this correspond to? Sure, I could take a look at the headers and try to match it to one another, but a better example of how I could view this data would be here in Kaggle. This is where I actually grabbed this data from. And it's a pretty good place to go and grab a bunch of experimental data if you need to, just to work with it and read the table as to what's going on in the data set and so on. Well, let's go and take a look. So here in Kaggle, we can see that the purpose of this data set is for us to actually be able to guess essentially what is a student's accurate grade. And it does a pretty good job at telling me what information I have here. So it tells me, hey, you're going to receive a student ID. Every single one of them is going to be an integer value. And you can see there's up to 500 of them, probably way more. All right. We can see that there's 51% females and 49% males. It's one percentage, so we really don't have to account for like skewing our data as far as accounting for that 1%. And something really important about these graphs that they show us here is we just want to make sure that they're not too far leaning towards one another. This is a pretty good graph that shows us, hey, everything's pretty well balanced out. Here's all the age groups, the study hours, attendance, and then GPA. GPA being our target. All right. So that's what we're trying to guess. We're trying to guess, hey, what kind of GPA would the student achieve if they take in these attributes? Now, this is a pretty good example of a balanced data set. Well, what would be a good example of an unbalanced data set? Now, this data set is one of the data sets that I utilize to learn machine learning myself. And although a good data set, it definitely challenged me in the fact that I didn't understand that skewed data would mess up my project. All right, well, here I have a bunch of levels for pH, and essentially somebody went out there and collected a bunch of information regarding different bodies of water and determined whether it was actually drinkable or potable or not, right? Where zero would be something that is potable and one is, oh, excuse me, zero is something that is not potable and one is something that is potable. Now, if you take a look at the data here, the data is pretty skewed, all right? There's a very small percentile of successful bodies of water that were came out to actually be potable. And there was a massive amount of data collected that was not potable. So my model, when I first trained it the first couple of times, it was very good at guessing water that isn't potable, but it had a lot of trouble recognizing what kind of bodies of water were actually something that I could drink from. So I had to go through the process of balancing the data, taking out a considerable amount of the data. There's a couple of different processes for this. You could either take out the data um, that you have from the opposing side. That's the simplest process. But if you do something like that, you're also losing quite a bit of your data that you want to work with. All right. So it's kind of like a double-edged sword. If you want to do it, yes, it's good for speed, but at the same time, it's going to harm you overall because you're not going to have so much data to work with. Now, if I want to keep the data and I want to also account for the data to be balanced, then I would go into the process of generating data. And I would generate data. I would only utilize the potable water. And from that potable water, I would try to replicate those same conditions in different possible bodies of water. I would generate this myself utilizing an algorithm or a tool within scikit-learn. And that would create quite a bit of data entries for me in order for me to balance out all of the ones that were false and all of the ones that were true. All right. Does anyone have any questions about the data, where it's come or why it's coming in from, how we collected data, and how this data is important in order for our machine model to actually be able to learn? All right. Doesn't seem like we have any questions. If we go back to our drawing here, that data that we just showed or that we're looking at is our features that we'll be placing into our neural network and then expecting a target to be an output, which will come out from our neural network. Now, in part one of our lecture, we're going to concentrate in the aspect of working with data. We're going to go ahead and install PyTorch. And after installing PyTorch, we're going to go ahead and divide this data with pandas, work with this data to try to analyze it and create some data frames. And we'll see how data can get pre-processed and cleaned up. So let's start off with the process of actually installing PyTorch. Well, what is PyTorch? Let's take a look at it. PyTorch is essentially utilized for deep learning or machine learning as we know it. It's a very popular framework because it's built upon Python and it leverages the language in general, right? It does a lot of mathematical operations that happens in the background, and it does that through a specific data set named tensors. We're going to take a look at tensors here shortly. Now, there's a couple of other popular frameworks that you can utilize. PyTorch is specifically famous for working within Tesla. They work inside of the Tesla's image recognition system. Um, Essentially, what happens is that camera inside of a Tesla is always continuously sending images to this model, and this model is continuously identifying all of the objects that are within that image. So it breaks down the image into a bunch of tiny squares. It reads their RGBA values. And then for all those RGBA values, that's what gets fed into the neural network as an actual data set. It then breaks down the entire image and then returns to us what it is that it's recognizing, whether it's recognizing a light post, a person, a sidewalk, etc. All right. Well, let's get started with PyTorch. Now, this framework has a pretty nice interface for you. When you go into get started, it's going to choose for you what would actually fit your machine the best. But in the case it doesn't, make sure you're utilizing the stable version. Currently, I'm on Mac OS, so I'm going to stay within Mac. If you're within Linux, just change into Linux. If you're within Windows, just change into Windows. I don't recommend utilizing CUDAs, just stay within the CPU aspect. All right. Now we're going to install through pip. We will install through Python. And there's our default language. Or for me, default. If you're on another system, you would just pick CPU. All right. Go ahead, Tom.
Yes, sir. When choosing the OS, if you're on like WSL, uh, does that change like your OS since we're running in a VM? So like for us, would we choose like Linux or would we still choose our like actual base machine?
Yeah, that's a great question. So you actually choose what your VM is running on, which would be Linux in that case. Does that answer your question, Tom?
Yep.
All right, perfect. So here I am on Mac. I'm going to grab my command for pip install. I grab Torch Vision. I come over. Notice how my virtual environment has already been activated. I'm going to install it. The installment process continues to happen. Might take a while. That is a-okay. All right, and there it is. PyTorch is finally installed. Now that PyTorch is installed, I can connect it to my virtual environment, or excuse me, to my Jupyter notebook. Excuse me. Now, I'm going to go ahead and run which Python 3. And here in which Python 3, it's going to return to me my path to my Python environment. I'm going to open up the command palette with Command Shift P, select my Python interpreter, enter interpreter path, and paste that path. That will set up VS Code to recognize my virtual environment. So now I can select kernel, Python environments, and you'll see that my virtual environment is recommended. All right. So I've installed PyTorch, but how do I know that PyTorch is actually installed and accessible to me inside of Jupyter Notebooks? Well, I could quickly check that by importing Torch and then printing torch.version. I could see my handy dandy AI buddy is trying to give me a hand here, so let me turn that right off. And when I execute this, it's going to take probably a couple of years. There it is. I can see that I have version 2.9. All right, let's hear questions. Go ahead, Rick.
Yeah, my question, and I could answer my own question, but whenever you do that, is it installing it in the environment or is it installing it system wide?
In the environment. So the
Okay.
environment itself, as long as it's activated, it'll be accessible.
Okay. All right.
All right. Any other questions? Sorry, I just saw Tom's image. Okay, perfect. Doesn't seem like there are any other questions. So now we have PyTorch installed and we're able to work with PyTorch. Now, again, PyTorch has a specific data frame called tensors. We'll take a look at that later on and we'll dive deeper into PyTorch as we need to. Now, the real tool that we'll be utilizing to read this data is going to be pandas. We're going to scratch the very surface of pandas, but know that if you're interested in getting a data analytics job, or if you're interested in just working with data in general, pandas is pretty much going to be the backbone of any sort of data-driven environment or job that you may get out there. So with that said, let's go ahead and pip install pandas. Pandas will get installed. On top of pandas, if you're actually interested in data-driven stuff, you might also end up utilizing something like NumPy. So that's something out there as well. And here we'll name this deep learning. And then we'll go into working with data. So in order to work with our data, let's break out our TLDR one more time. When our data comes in, it comes in as a pure CSV file. We want to turn that data frame, or excuse me, we want to turn that CSV file into something that we can work with within Pandas by turning all that data into something called a data frame. Now, once we have this data frame, we want to also account for null values, or excuse me, I think we're going to actually divide our information first. Because as our data comes in, you'll notice that there is a difference within what's inside of the data. Inside of the data, we have such a thing named targets, or, and we have something called features. Now, features are essentially what the attributes that will lead us to our answer, meaning that there may be many of them. And our targets would be what our one-off score, our output should be. So if we take a look at our example, our features may be many. Our output would only be one. In this case, it would be this fuchsia one at the bottom because it holds the highest percentage. We'll divide it into features and targets. After it gets divided into features and targets, we're going to grab features themselves. Oh, hello. And we're going to take a look at the features to make sure that the data is balanced. Account for null values. And then we're going to standardize our data. And that kind of goes into the process that we talked about yesterday a little bit, where we have or excuse me, I don't think it was yesterday. Let me see here. All right. Unfortunately, I can't find that drawing that I'm referencing. So let me draw it out again. We would have our top and bottom limits. Where data becomes mapped. We may have some points that fall outside of the norm. And what we're essentially going to do is we're going to correct those points by squeezing them and bringing them in back within the top or bottom limits of our data. All right, go ahead, Tom.
So when we standardize, does that affect any of the other data points by moving them in closer towards the middle line?
That's a good point. To answer, or that's a good observation. To answer your question, yes. We're going to see that our entire data gets mutated. There's a lot of math that goes in the background And essentially what it does is it makes sure that everything stays even out and calculated in a way where skewed values won't affect our data set, but the values that are very minute can still have the same impact that they should have. Right? So for example, a value like this, it's so close to the center that it might not really affect our data set. Well, we would want something that falls outside take the same amount of impact as something that falls close to the center. That way our model isn't just completely bouncing completely to top or completely to bottom. So everything gets standardized to be within that one sandwich. Does that answer your question, Tom?
Yep.
All right. Okay, awesome. So let's go through this process of actually recognizing our information, squeezing out our data, and bringing it out. So again, we would have to read our data, not with CSV, but with Pandas. We then have to recognize features and targets. After recognizing our features and targets, we have to account for null. And then we can go through the process of standardizing. So let's start actually doing some code. Here, I'll import pandas. And I'm just going to give an alias of PD. Now grab my data by saying PD dot read CSV. Pandas has a function named read CSV that will quite literally just grab our CSV and be capable of reading it. And all I have to pass into it is the path to said CSV. So I could pass in student performance. And I can just take a look at the data from that data frame. Data, read CSV. Let's see here. No such file directory named student performance.csv. Well, let's see. What are we looking at? Student performance. What did I write here? Oh, out the .csv. And here's our output. I'm gonna go ahead and bring this to a bigger screen so that we can take a look here. You can see that I took our CSV file and created a data frame. This isn't a list of dictionaries. This is, again, a special data structure that comes strictly from Pandas. It shows us our top 5 entries, and it shows us our bottom 5 entries, with a total of 2,391 entries that we have for data to work with. All right, does anyone have any questions about how we were able to grab data? Okay, in that case, let's start moving into accounting for null. Well, here we have data dot is null. Let's see what that returns. We can see that data dot is null returns false, false, false for everything. But it doesn't really give me an accurate count, and I'm really not going to go into the process of checking every single one of them, right? If I wanted to do something like that, it would take a considerable amount of time, and there's 2,391 rows. So maybe there's a better way of seeing this. Well, I can simply just add sum to the end of that, and it shows me for every single row a total sum of any null entries. So currently, there is no null entries. So I don't have to worry about it, but this is a fundamental step. So I'm going to provide this line of code for us. In the scenario that you're working with a data set that does have null values, you would want to fill it utilizing fill null with data.mean. And then this in place equals true means in that exact location where we see a null value. Excuse me, I seem to have allergies this morning. In that exact location where we find a null value, I want to replace that null value with the mean of that specific column. So we'll take a look at the entire column, all of its values. So let's say if we're looking at age, it would calculate what the mean is, and then we'll fill in that null entry with the mean of that row, or excuse me, that column. All right. Go ahead and restart my kernel, make sure everything's good, that I didn't actually execute that process of filling in for null because we didn't have any null. Okay, great. Okay, so far, we took our CSV file, we accounted for null, and now we're going to go into the process of recognizing our features and our target, where our target is the grade in the class, and features is everything else above it. So let's take a look here. Or excuse me, GPA is not our target. Grade class is our target. All right. So here we open up another block of code, and now we can actually start realizing what information we're working with. So features is going to be everything within our data frame, with the exception of grade class. And then we also want to pass in this argument called access equals 1. We're essentially saying, I don't want you to mutate the data frame just because I'm removing this information. I still want you to keep the data frame in the same exact format. This access can change the access of your data. All right. And now if we take a look at features, you'll see that features outputs everything with the exception of grade class. We have all the way over to GPA. So we're able to identify all of our features. Nice. Now there's also meaningless stuff that we don't need. For example, this is student ID. It's just going to be an incremental value that rolls all the way to the bottom. And we know that it's not going to have any sort of relationship to the output of our actual student performance, right? Their ID has no input into their performance. So we can also remove that. We can say, hey, we also want to drop student ID. Now this raises the question, what else can I drop? And how do I know when to drop it? Now, we're not going to dive into it here in Code Platoon, but there is something called a relationship graph. And essentially in this process, what you'll do is you'll feed all this data through a graphing process, and it's going to graph how strong of a relationship an input may have to the actual output. And from there, you can determine which one of these features you can drop. It'll determine, hey, maybe extracurricular has no impact on the actual output of what a student's grade may be, and that could possibly be dropped. Some of them may even point out that you didn't expect it at all. Maybe after we graphed it, it tells me, hey, the student ID actually has a huge relationship to what the output may be. But in this case, I'm here making a huge assumption saying that the student ID wouldn't actually interact with our information. All right, so now that I have my features, I can go into recognizing my labels, where my labels is essentially my one column from data, which is named grade class. And I'm actually going to take a look at labels here. So as labels come back, we can see they're coming back with 2.0, 1.0, etc. Now they're coming in as floating numbers. When it comes to targets, or excuse me, let me go ahead and rename these as targets. When it comes to targets, you want to make sure that information matches. Or excuse me, you want to make sure that you're working with whole integer numbers. Whether it's a binary model, whether it's a multi-classification model, you're always going to be working with whole integer numbers. So if we're seeing something that's floating like this, we want to cast it. So I'm going to go ahead and say s type integer. And now we have our 2, 1, 4, 3, and so on to view all of our targets for the one column of grade class. Okay, so if we go back to our TL draw, currently we're in the step of dividing our features and targets. We grabbed our CSV data, we grabbed our data frames, we accounted for null, and we haven't standardized our data just yet. Up to this point, does anyone have any questions over what we've done with our data sets? Okay, it doesn't seem like we have any questions. Now, again, the process of machine learning is not as fun as development because it's a lot of repetitive process. The next topic that we'll be diving into is standardizing our data. And we're going to be doing this with scikit-learn, which we'll take a look at what that is right now. And we'll be grabbing standard scalar from scikit-learn to be able to do this information. All right. Let's take a look at scikit-learn here. Now, scikit-learn, well, you can come over and immediately it gives you all of these graphs. It references classification models. There's regression models. There's such a process called clustering. Here's some pre-processing for pre-processing inside of data. This is essentially just a massive library that you can utilize to be able to grab different classes, different functions, a tremendous amount of tools that relate to machine learning. Now, specifically today, we're going to concentrate on grabbing their tools made for text, or excuse me, not for text, for pre-processing data. But before we do that, we want to get started by just simply installing scikit-learn. All right, here's showing me a couple of transformers and all kinds of other stuff. So maybe I missed the part where it gives me there it is, installation instructions, Mac OS through pip. I'll go ahead and share this information with everybody on Slack. I'm sharing it here on the Buffalo channel. That way you guys can come over and grab this. And here's my command that I want. I want to say, hey, pip install -u scikit-learn. So I come over to my virtual environment. I run pip install -u scikit-learn so that I have scikit-learn installed. Now, while that's installing, let me go ahead and look up standard scalar. All right, pre-processing standard scalar. Here it gives me a little bit of information as to how it works, the information that it's going to take in as an argument for that class. And then it gives me a mathematical process as to how it actually tries to standardize my data. If you want to read through it and get yourself a little bit familiarized with what's going on under the hood, which I strongly suggest, that's what really gives you the edge when it comes to all of this machine learning information. Otherwise, you're really just kind of copying and pasting code. So I would strongly recommend going through this documentation and getting yourself familiarized with what's actually happening under the hood inside of standard scalar. the specific function that we'll be utilizing today is going to be fit transform. You'll see that it takes a couple of parameters and it tells you what exactly it is that it's returning. All right. Now, let's apply it. We have all of our features that need to be standardized, not our labels. Only our features need to be standardized. I'll say that again, not our labels, only our features need to be standardized. Just like we see in our drawing over here, at this point, our targets are being left alone, and all I'm working with is our features. So I'm going to say from sklearn, which is scikit-learn, dot processing, or excuse me, pre-processing, import standard scalar. And once I have standard scalar, we can see that that's a class. So I'm just going to make scalar be equal to an instance of standard scalar. And I'm going to make my features to be scaled. So I'm going to grab scalar dot fit transform features. And then finally, I could take a look at my features that come back from this. Okay, well, it's no longer a data frame now. Now, what I'm seeing being returned for me is going to be a NumPy array. Now, NumPy arrays are special in the fact that they directly translate with tensors. And the way they're set up is to quickly be able to do math with other rows of data. We'll take a look at that math later on, but multiplication between two of these arrays is a lot easier to achieve. Also, there's cross multiplication. So, for example, where you would want one input to multiply times all the inputs of the secondary array. And there's a couple of other functions that happen within data that is just going to be a lot easier to account for utilizing tensors and NumPy arrays rather than utilizing something like a pure Pythonic program, but would have to write all that math from scratch. Right. And now our features have been standardized. Does anyone have any questions regarding how we grabbed our data, divided our data, and actually, let me go ahead and change this up a little bit because before we divided our data, I would say features get standardized, but our entire data, we account for null, balance, and the standardized portion needs to leave. All right. So does anyone have any questions over how we grabbed our data from the CSV, created a data frame, we then balanced and accounted for null, grabbed our features, and standardized our features? Okay. If no one has any questions, let's continue moving on. Well, now that we've standardized our features, we have targets and features that are being delivered to us. Now, from those targets and features, we want to create testing and training sets. Where our training sets would be about 80% of our training data, and our testing set would be about 20% of our data. So we'll have our training set, which again is about 80%. And then we'll have our testing set. Which will be about the remaining 20%. So we'll say 20% for testing and 80% for training. Now, when we divide this training and testing data set, we're gonna divide them and match each one of those NumPy arrays to the correct feature. Even though we standardize our data, everything's still in order. All of our features are still in order, and all of our rows are still in the descending order that we initially got them from the data frame. So all we need to do is a 1-for-1 match where row 1 would match with row 1 of our targets. Okay. Now, how do we create this testing split? Let's take a look here. I'm going to come back. Actually, I'm going to come over here. The tool that we'll be utilizing now is called Test Training Loader. No, it's Train Test Split. So Train Test Split. Excuse me. You see that this comes back from model selection. And what train test split does is it returns to us 4 different arrays. So you can see that it returns a list. That list has 2. List containing training test split. Okay, awesome. We're going to pass in a couple of arguments to it, and we'll get back all of the information that we need. It's actually going to return to us 4 indexes. I wonder why it's returning and why it's saying here that it returns 2. All right. We're going to create our training and testing split. Again, from scikit-learn. We will import train test split. Now, train test split returns 4 arrays. We'll see the parameters that it takes in right now. But each one of those arrays would be 2 training and 2 testing, where one of each falls into either the test portion. This will make more sense once I actually write it out. I apologize. If I try to write this out in just plain English, it's not going to make sense. All right. Let me go ahead and grab this. I'm going to say from sklearn.model selection. I want to import train test split. Now in here, let's do train test. And I'm just going to pass in train test split, where I'm going to pass in all of our scaled features now. So I currently haven't saved as features. I'm going to pass in all of our labels, which are as integers. And I'm going to specify the test size. Well, the test size that I want to work with is going to be of 0.2, because we only want 20% for the test, meaning that my training size would be of 80%. And then I'm going to pass in something called a random state. And I'll cover what this random state is here shortly. The standard argument for random state is 42. Again, I'm going to cover what that is here shortly. Okay, and then I'm just going to simply, let's take a look at the length of train test. Well, if we take a look at the length of train test, it returns 4. And if I try to actually look at what train test is having inside of it, it's going to show me multiple arrays nested within one another. Okay, well, I have 4 arrays. What are those 4 arrays? Well, at index 1, and I'm actually going to put this in an F string here. Instead of index 1, we would be index 0. At index 0, we would have our training features. At index 1, we would have our training targets. At index 2, we would have our testing features. And finally, at index 3, we would have our testing targets, where these would account for 20% of our data, and these would account for 80% of our data. So we could just simply dissect it by doing this number. We can say, hey, I want my training features, my training targets, I want my testing features, and my testing target to be equal to train test. And we're essentially just grabbing at index 0, we would have our training features, just like we specified up here. At index 1, our training targets, testing features, and so on. And that would give us our outcome here, where 80% of our features and targets would be grouped together, and 20% of our features and targets would be grouped together, all within their own training and testing split. If I execute this, we'll see that nothing happens. If I go to actually take a look at training features, and I run that, we see one singular numpy array, which is what I expected, rather than having 4 numpy arrays. All right. Does anyone have any questions regarding this train split function? Okay, let's talk a little bit about this random state part. Now, what this random state is saying is I'm essentially chunking my data by blocks of 42. And after chunking my data by those blocks of 42, I'm grabbing that block of 42 and I'm randomly placing it throughout my data set. So I may have 2 of them, where one of them maybe is at index 1 and this one is at index 2. I may have, because we have so many entries, it's going to simply chunk them by 42 and then take those 42 chunks or as many chunks as come out and then randomly shuffle them around. Now you may wonder, what's the point? I don't understand. What's the whole point of randomly chunking information and turning it inside out and then randomizing it like that? Well, this actually helps your model learn a lot better. And the way I like to think about it is of me taking a multiple choice test, because that's what essentially the machine is going to be doing. It's going to be taking a multiple choice test where it has to choose between the options of A through D, right? Well, if I'm taking the same exact test, and after every test, I'm also receiving a detailed review of the test. So I turn in my test, And I get told, all right, let's break down the questions. And we go, question one, this is the answer. Why is it the answer? And we review it. And I end up failing the test. Well, then I get told, all right, now you have to take it again immediately. I take it again. I fail a second time, and I get the same exact review. And every single time I receive the test and I get the review, I'm receiving the same exact test and I'm receiving the same exact review over and over again. Now, at that point, am I learning or am I memorizing?
Memorizing.
Yeah, at that point, what I would be doing is just memorizing information. I wouldn't be actually learning anything. And that's what we're trying to avoid with the machine. We're trying to make sure that our machine isn't just memorizing patterns, but rather learning how to recognize these patterns. So that random state becomes very important when we're chunking information and turning it inside out like that. All right. So now we have our training and testing split. The final portion that we have to work with here is going to be data loaders and tensor data sets. Okay, so we've been working with our machine. We have all of our testing splits and everything set up. Well, now we actually have to feed these two testing splits into something called a data loader. And the way I like to think about these, I don't like to overcomplicate them and try to think about them because they're essentially just another layer on top of the tensors that we're already working with. So I would like everybody to think of them more as of a function, where our data loader takes in a tensor data set and what this is going to do is essentially going to take all of our inputs and feed them to our neural network. So let me actually grab our neural network from up here, bring it down. Tensor data set is what feeds our neural network. And then a tensor data set I would like to say that it's just a transformer that turns numpy arrays into tensors. Right, so we're going to feed all this into the tensor data set. We're then going to pass it into the data loader, and our data loader will feed our neural network. All right. A little bit of layering that we have to do here. Now we're actually going to start utilizing our tensors. So I'll bring in this information. I'll say from torch import tensors as t. This will give me the tensor itself. I have to transform all of these numpy arrays into tensors. So I'm just going to Command C and bring that down here to make sure that I don't lose it. And now I'm just going to say, all right, I have my training features, which would be equal to tensor training feature. Where my data type would be a torch dot float 32. And I have torch imported at the very top of this file. I'll then grab my targets. I'll turn it into a tensor. Now remember, our targets are a little bit different because our targets are integers. So we actually have to turn them into numpies. So I'll say 2 numpy. And then specify that my data type will be of torch long. I could grab my testing features, make that equal to a tensor. Well, I'll grab my testing features. My data type would be of torch float 32. And then finally grab my testing target, which would be a tensor of testing target 2 numpy of d type torch dot long. I could probably write a function that would do this for me, but there's no need to overcomplicate things, right? So I could just now, let's go ahead and print training features at index 1. And here we'll print training features at index 1. Okay, so yeah, now we're working with tensors, so it's not going to like this. That makes sense. All right, looks like we're getting a little bit of an error here. Cannot import name tensors. D-type torch long. Object has no attribute to numpy. All right, interesting. Looks like I'm crashing into a bit of an issue here. We'll get to that here shortly. Just gonna remove this to numpy and see if that will do my trick here. Could not join the shape object type series. All right, I'll dive back into this here shortly once we're done with the remaining of our code block. Let's hear it. Go ahead, Arnold.
Yeah, so for the importing stuff, what is the difference of the one that you use from the from torch.utils.data import data loader and tensor dataset?
Sorry, could you say your question one more time? I don't think I actually understood it.
I just noticed that you use a different importing for the tensor dataset, and then on the curriculum, it has a different importing names. Does that matter? Because in the curriculum it says from torch.utils.data import data loader and tensor dataset.
I haven't gotten to that portion of the curriculum just yet. I'm actually about to dive into it right now, Arnold. But good looking out. Thank you. I appreciate it. All right. Now, in this portion, we're going to actually utilize our tensor loader, which is going to fail because I haven't been able to fix that just yet. But we can still get through the code base itself. We're going to utilize our tensor dataset, which is going to take in both our features and labels for either training or testing. And then we're simply going to feed this tensor dataset to our data loader, which our data loader will take in a tensor dataset, whether we want to shuffle, and a batch size. All right. So now we can actually import, and this is the part that you were talking about here, Arnold, where we're going to say from torch.utils.data. We're going to import data loader. And we'll grab the tensor dataset as well. Now, again, for both of these, we have our training, and we could call it data set where we're going to create our tensor data set, bring in our training features and our training target. We'll have our testing data set, which will take in a tensor data loader, or excuse me, a tensor data set, which will take in our testing features and our testing target. And then finally, we have our training loader, which will feed our neural network, which will be a data loader that takes in our training data set. We have our testing loader, which again will be a data loader that takes in our testing data set. Now, for both of these, there is another argument that we want to add. We want to add something called a batch size. And the batch size is essentially the same thing that we did inside of the testing loader. We're dividing it by groups of 32. And for every single group of 32, we're going to shuffle it yet again to ensure that our model will actually learn and not just memorize information. Now, let me see if I can figure out where this typo came in from or where this issue came in from. I specifically remember running into it before, so I will find it. Let me see here. Contour triple tensor, testing target, D-type dot could not determine series. But I have a problem with that one. All right. Well, currently we've been going for an hour. Let's go ahead and take a 10-minute break. By the time that 10-minute break is over, I'll have this figured out, and then we'll continue on with our lecture to actually building our neural network. Thank you so much, everyone, and I'll see everybody back in 10. All right, welcome back, everyone. Now, there's a couple of mistakes that I made here. The first one was starting in my training loader, or excuse me, my train test split. One, I created my targets, and I put this as labels, so I didn't actually pass in the correct variable there. That's the reason why that was failing. Not only did I do that, but also the way I described what it gets returned was wrong. So we get back our training and testing features, and then we get back our training and testing targets. It doesn't actually return them in the order that I described, which also caused a couple of errors later on. Now, because we're already working with a NumPy array, there's no need to turn them into NumPy arrays again. So we could skip that toNumPy function altogether and just pass them in straight into a tensor, specifying that we're working with a torch long because this is an integer, and specifying that we're working with float 32 because we're working with a floating number that we want accuracy up to the 32nd decimal place. Boom. All right, after that got completed, we can come down here, create our training and testing data loader. And if we actually take a look at our testing loader and execute this information here, oh man, it won't actually show it to us, which is unfortunate. But essentially what we have here is going to be an array of arrays, where inside of each array, we have a data set. And this data set gets fed where each one of these data sets actually holds our features and targets. So that's what gets fed into our neural network. That's the whole pre-processing portion of our entire neural network to be able to be up and running. Does anyone have any questions regarding the pre-processing of data? Let's hear it, Chris.
I know we passed it a while ago, but I was just curious if you ever came across skewed data, what kind of methods would you use to normalize it?
Yeah,
Would
that's a
it
great question.
just be that standard scalar, or would you want to do that before you do the standard scalar?
If you have skewed data, as in you have too much of one output and you want to balance it out, you would do it before you utilize the standard scalar. And there's a couple of different methods that you can utilize. You could either just decide to cut out data and even it out. Like you could write a function that will say, hey, for every positive output, I want to have the same match for every negative output, right? And then anything above that, I want to cut it out. So I have 500 positive, at the 1,000 negative. Well, I'm just going to get rid of 500 negative and just have 500 and 500, right? Or you could actually generate data where you would utilize the 500 positive outputs that you have it run through an algorithm, and that algorithm will essentially populate another 500 entries that you can utilize to be able to fill in that gap and then have a balanced data set. Does that answer your question, Chris?
Yeah.
All right, perfect.